Hi, I'm Connor Harris. I'm a CS50 CA at Harvard.
I'm Stephen Krewson. I'm a TF for CS50 at Yale.
And we're going to talk about some technologies that you might want to use if you're interested in doing a final project or really anything with music. We're going to be focusing on, first, a programming language called Haskell. It's a functional language, so the paradigm is very different from C or PHP or other imperative languages that you've used already. And especially on a library written in Haskell called Euterpea, which can help people with writing music functionally, basically. And Stephen will walk you through a great example of that. After this, I'll introduce you to something called Lilypond, which is a technology for typesetting music. It's sort of like LaTeX for music, if any of you use LaTeX for math classes or other PSET classes or what have you. And so I'll give you, again, some simple examples of that and point you in the general direction of some better resources.
In addition, we thought it would be cool to kind of set up a little bit of hints toward a pipeline between Euterpea-generated MIDI files and Lilypond. So we provide some instruction on scripts to do that are provided with Lilypond, just to keep it open source and get a pipeline going.
Again, that we should emphasize these two technologies, you don't have to use them together. They're not designed to work together, though they do very nicely.
Right. And totally free.
So, acknowledgements, just read that.
Duly noted. Thanks to those folks. This I'll linger on just for a moment. The installation process is a little bit tricky. We have a README on the GitHub that you can take a look at. Just email me if you have any questions. But we'll run this on the assumption that this is working for everybody.
And if you can't get Lilypond to work, no big deal. There's no live compilation that will be involved, but at least on my end.
Yeah, Haskell and Lilypond should both have installers. Euterpea is downloaded as a package, so on and so forth. OK, so we're talking about computer music, and this is just a very 50,000-foot view. There's a few different aspects of it, and this is rough and is going to obscure some detail, but we could think of something like algorithmic composition, using algorithms, using code to generate some type of maybe a self-similar sequence of notes, or maybe notes under some constraint. And then those could be performed or interpreted with analog instruments or anything like that. But the composition was done algorithmically. But of course, maybe the area of computer music or digital music we're more familiar with is digital sound synthesis or digital sampling and digital recording. A lot of digital instruments are done through digital sampling. In fact, we'll be using one of those in the form of a sound font library later. But there's also something called digital synthesis that came out of the late 70s and into the 80s with Yamaha and John Chowning at Stanford doing FM synthesis, or frequency modulation synthesis, where you had a carrier signal and a modulating signal both in the kind of audio spectrum. But what we're focused on today is something called MIDI. And of course, algorithmic composition. We're not going to make instruments, but we're instead going to make some music, and then that will get interpreted by some instruments that are conformant to the general MIDI standard. So what's MIDI? I'm not going to get too deep into it, but MIDI is a data transfer protocol, and it's a kind of a guide across different companies and industries for organizing sounds or patches. So we'll see that there's a MIDI standard for all the different percussion sounds, and MIDI recommendations for all the different types of synths or different types of all the instrument groups in an orchestra, say. You're probably familiar with the 0 through 127 MIDI messages. A MIDI signal is typically one bit indicating whether it's a data or a status packet, and then there's 7 bits of a signal. And these can control everything from volume to kind of the action or pressure on a particular key if you're performing with a MIDI controller, as well as, of course, notes. And of course, MIDI has been extremely useful because it's a way to wire together or daisy chain a bunch of MIDI hardware devices. I have like 7 or 8 back at my house. It gets really complicated, but it's really powerful. And it's really old. It's from the early 80s, and it's really nice and small.
Yeah, all the classic Nintendo video games would probably have MIDI files for music, for example.
Right. Here's an example of general MIDI, showing MIDI as a kind of general protocol. And I think we can think of the difference between the specification that there should be something like these instrument sounds and the actual realization of those instrument sounds in like a sound font or a particular MIDI synthesizer as being the difference between maybe like a typeface, which says in general this is the design of this particular way to represent characters, and a particular font that has a specific size and timbre, and there's a realization of the typeface.
Maybe a better comparison would be the Unicode standard says, like, it gives a number to every character in really every language in the world, or a vast set of scripts of languages in the world. And then those are rendered into something graphical by various font packages. Analogously, you could think of MIDI as the Unicode of sound. And then it's just a list of, or a big stream of events and instruments and whatnot, and you have to have a separate program like a typeface to render that into something that's audible.
So why Haskell? Haskell is a functional programming language, very advanced, very different from C, very different from PHP. And we're going to see that there's an ease of function composition in Haskell that will allow us to sort of breeze through composing or typing up, transcribing something like Frere Jacques, this kind of simple song that has a lot of parts in it that are self-similar or repeating. And yeah, so this will be some of the motivation for why we're using Haskell, in which functions are first-class citizens. And I wanted to extend this a little bit. It's a little bit easy to notate Frere Jacques in Haskell, but what if we wanted to add a drum part to it? What if we wanted to try to make something like a Roland 808 or 909 drum machine, where you have about 16 different steps? Usually these are thought of as like 16th notes. And you can control the global tempo, and you can pick out a bunch of different percussion parts, a bass drum, a clap, different snares, open and close hi-hats on these sort of channels. And then you can EQ or adjust their volume. And we'll see a nice way in Haskell of sort of representing this step sequencer with all the various cool things in Haskell we can do with generating lists and filtering over lists, mapping over lists, mapping functions over lists. And a quick apology. This is a very cursory and overly quick sketch of some of the aspects of Haskell and Euterpea, which is a domain-specific embedded language written in Haskell for musical types. So please do check out the code online. Fire up GHCI, which is the Glasgow Haskell compiler interpreter. And I'll be doing some of this in a little bit so you can see how it's done. And this allows you to load in with the syntax is sort of colon and then the command. You can load in files. You can use browse on those files to see all the functions that exist in a particular module. And then, as we'll see, types and type classes are so important in Haskell. So you can always check, especially if you're working in a new DSCL like this, what is a music type? I know about the way numeric types work in Haskell, but I don't know much about music. But you can explore the way they're defined by using this T or type command and then calling in a particular function or data object.
Yeah, because if you thought C and like Clang was hard-assed about types, you have no idea about Haskell.
Yeah.
The great thing about Haskell is that if you can get your code to compile and it passes all the type checks, it's probably right, because the type system is so strict.
Yeah. So I just want to go through, and again, this is not doing it justice, a few of the features of Haskell that, at least to its creators, and it was created in the late 1980s by a bunch of people, a committee of about 20 people, thought were important. And the first thing they listed in the kind of paper that described the genesis of Haskell over the first 20 years or so was that it was lazy. So what does this mean? Well, it means when we have some kind of expression, we need to evaluate it. And Haskell does this in a call by need way, or a non-strict way. That is, if we have a bunch of components of our expression, we try to delay the evaluation of those subcomponents until the absolute last minute. That is, until we actually need them. So this means, which is really cool, especially for like if we're thinking about the abstraction of a musical step sequencer. You turn it on, and you start running a step sequence if you ever work with a drum machine, and it just goes forever. So it'd be really nice if we could emulate that in Haskell, and we can do it with infinite values, in particular infinite lists. It's very easy to type an infinite list in Haskell. You could just use the syntax down here where you see 1 through 3, remove the 3, 1 dot dot, and that is an infinite list of all the natural numbers extending on as far as you can imagine. And I want to introduce a concept of folds right away. And again, the purpose of this seminar is not to learn about folds in Haskell or higher order functions, but I just want to introduce it to give an accurate sense of how weird Haskell is and how powerful it is. And in particular, we're going to be, when we do our different drum parts, we're going to be manipulating lists of numbers, folding them onto each other. And to do that, we'll be using maps and folds. There's a right associative fold, which is this one right here. 1 minus the quantity, 2 minus the quantity, 3 minus 0. And the syntax for a fold, you give a fold a kind of base value and then an operation. In this case, addition or subtraction. I've shown both cases. And then there's an accumulator that accumulates over the entire list, applying that operator, plus or minus, and then accumulating it. So this will be if it was called with foldr plus of 0, it's starting with 0, we would then sum all the numbers in that list. And that's a list from 1 to 3.
Yeah. So to put it another way, foldr takes 3 arguments. There's a function that itself takes 2 arguments. Then there's a starter value, and there's a list of values.
Right.
And what you do is you take starter value, first value, put them into the function. What do you get out? Take that, feed that into the function with the second value. What do you get out? Take that, feed that into the function with the third value. And then if you go down this whole list this way, you're going to get eventually some singular value that's of the same type of what you started out with, another same type as things in the list, and then that's the return result of foldl, or foldr.
So particularly these are higher order functions because they're taking another function as one of the arguments.
Yeah, if you've used certain other languages, I know R, the statistical language, has this called reduce. You might have similar functions in other languages, just called different things.
Right. And what's nice about foldr in this instance is that foldr can work with infinite lists. So in this bottom, this P5 is generating the notes that are turned on in the step sequencer for some drum part, the 5th drum part, and maybe it's a conga drum or something. And this is a deliberately sort of obtuse way of writing this, but it's fun because it demonstrates a lot of things about Haskell and Euterpea. So foldr of this colon is just an operator that pushes things together on a list. Call it on an empty list, which is just the empty brackets. And I'm calling that on this infinite list. This is actually 2 lists added together down here. The list 1, 6 dot dot is 1, 6, 11, 16. So Haskell, in just a few characters, you can generate the entire sequence of numbers that are 5 numbers apart, stretching on into infinity. And I prepend to that this shorter little list, 3, 8, 21, just to show you how you can concatenate lists. And then I fold it on itself. And this ends up just being a kind of identity operation, but it's infinite. And foldr can do that because it lazily evaluates, as in the above. If we have a 1 and a 2 and a 3, we can just bracket off the entire rest of it. That won't work for minus or plus, but it will work for this colon identity operation on a list. So how do we practically use that if we have an infinitely long list of things? Well, Haskell provides a lot of functions, and look more into these in your own time, such as take, which says, OK, we're generating this infinite list, but we're just going to take some number of it. And in this case, we'll see this later in our drum machine code. Gn is just some kind of global variable for the number of steps in the sequencer. On the roll-in machines I showed you, that's typically 16, but I have implemented it with 32. It doesn't really matter. Haskell is also pure, so it has strong static typing that Connor alluded to. So functions are mathematical in the sense they're more mathematical that they're guaranteed to not access or change any kind of variable or perform input or output. So if you have a function, it's deterministic. It will always return the same value, and the state of the program will remain the same. There are, of course, monadic exceptions to this, but that's beyond our scope.
Yeah. What this means, though, is there are a few important design consequences of this. One is that it's very easy to parallelize Haskell programs, because if you have, say, a function that needs to operate on 1,000,000 values, if you know that the function will always give out the same value if you feed it a certain value, but like if you're evaluating f of 1, f of 2, then f of 3 or whatnot, f of 1 is not going to write out to a file or do something that will alter the value of f of 2. You can just split up this function to 1,000,000 different machines or 1,000,000 different threads or whatever, get all the responses back, get all the return values back, and then that's it. So very easy to parallelize things. The downside is that input and output especially fit into the type system in very complicated ways. We won't go into that right now, but I encourage you to look at some resources online if you want to learn about that.
So type classes. And this was, classes of types were kind of invented to solve a problem of operator overloading. So we wanted to have equality between different types of things. Of course, we could think of equality between numeric types is very easy to think about, but what about equality between lists? What about equality between tree-like data structures? And this is all possible in Haskell because of type classes. So if you define a certain data type, and here, these are musical pitches. We're finally getting to some computer music, right? So we have C, C sharp, and so on and so forth, right? They belong to a bunch of different type classes. EQ, they belong to the EQ type class. That means they support equality operations. So you can evaluate whether one sequence of musical primitives is the same as a different one. They belong to the ordinal class. That means there's an ordering to these. D comes after C. C sharp comes after C as well, right? They belong to the class show, which means they can be printed to a console or terminal. They belong to the class enumerated, which means that even though these are characters, they have an underlying numeric representation, starting at 0 and going off through however many things there are in here, 20 or so, or 30 or 40 maybe.
Right, and when we have a data type that derives, with that keyword deriving, a certain type class, it means that the compiler will try to construct something automatically. So maybe you'll want to define equality differently. You'll want to define C sharp as equal to D flat, for example. With this construction here, I don't think C sharp and D flat will be equal because the compiler will automatically say every different possible value is distinct from every other. So it is possible to override the default implementations of these type classes.
Right.
Again, look in the reference if you want to learn about that.
Right. And here, actually, this will be helpful for when we code later. We see some of the infix operators for sequential composition, parallel composition, and so forth, these pluses and equal signs surrounded by colons. That means we can play these different musical primitives one after the other. That's sequential composition. Or we can play them in parallel at the same time. So I could have a musical value and then this equals and colons infix parallel composition operator and play them as a kind of chord. And we're going to use this when we combine our drum part with our little Ferrajaka song to play these two sequences of musical values at the same time. Currying was the last name of Haskell Curry, who the Haskell language is named after. And this allows us a nice elegance when we're writing all these different functions or filters that we're going to be mapping over our lists. A function of two arguments, f of x and y, can be represented as f of x applied to y. So it's a function of one argument that returns another function of one argument. So this means we can map a function f of x over a list of y's.
Want to give an example of this?
Yeah, so I have an example right here from some of the things we will write. So replicate 2. Well, replicate will take one value, which is how many times to replicate something, and then we'll take a value, usually a list or something. So here, we're mapping replicate 2 over another list. So if we map replicate 2, if we replicate 2 applied to the first element of this list, and these are lists of musical phrases, we'll produce 2 of you sleepings, right? So are you sleeping, are you sleeping? So now we have 2, OK? But replicate takes 2 arguments, but because we're currying and then mapping, we can represent replicate 2 as having been returned as a function of one argument, just replicating twice. And then we're applying that to each element of this list of phrases. And concat is a Haskell operation for kind of flattening a list, because replicate 2 will produce a list of lists. And this is this intermediate form here. And so then we can concat or flatten that out twice.
Yeah, a simpler example of currying, if you'd like. Imagine f is just a multiplication function that takes 2 arguments and returns their product. So if you have it f4, 5, it's 20. But you can think of this as also, you have a function f4 that takes an argument and returns 4 times its argument, which is partial application with just one argument 4. And if you feed f of 4, 5, then it will give you 20.
Yeah.
And that's a simpler example of currying. It's usually one of the textbook ones.
Lambda expressions or anonymous functions are sort of another Haskell hallmark. So if we need to whip up a little function like replicate, but say it's not in the standard library, we can use a syntax similar to the following. And we'll kind of breeze over this. One thing you'll see a lot of in the drum machine is we're making calls to something called filter, which, like before, is a mapping of a function over a list. But it's a mapping of a Boolean function. So we have here an example of a sort of anonymously defined Boolean function that just takes a couple values. This is not, strictly speaking, an anonymous function, but it's defined with that syntax for brevity. And this just takes x modulo n.
Yeah, so f is a function of 2 arguments, n and p, that returns a function that is itself a function of one argument, namely x.
Right. I mentioned infix operators. What are infix operators? Well, infix operators are the normal way we represent operations, say, in mathematics, 2 plus 2, instead of the operator plus and then 2 arguments, 2 and 2.
It's called reverse Polish notation, which is a term I doubt any of you would know, but if you do.
Yeah, reverse Polish or prefix notation. But Haskell decided to use infix operators. So these are some of the custom ones that are defined for the Euterpea DSEL in Haskell. So this was sequential composition. This was parallel composition. And this was truncating parallel composition. And we'll need that with our drum machine, because we'll use the last operator in that little tuple there to play the drum machine along with our Frère-Jacques song. And our drum machine is going to be infinite. It just plays forever. But the Frère-Jacques song is not. It's not that long. It's just only a few bars. So we need to stop the drum machine as soon as the shorter musical value comes to an end. And that infix operator is super helpful with that. And infix notation like this is kind of nice because say you have a function like quote, which gives the sort of integer division of x by something else. Sorry, that should be a and b. You can write it as a quote of b. So if you put, or element is another example of this, x element in some list. If you put it in backticks, you can use it even though it's not a symbol like plus or minus or times. You can use the name of a function like that in backticks as an infix operator, which is pretty cool.
Yeah. Again, this is all just syntactic sugar, really.
Right.
It doesn't affect the core of language.
Right. So we see here, for the kind of last phrase of our Frère-Jacques song, I've played some little kind of chords or thirds using the parallel composition operator. This is sort of another way of saying some of what we've just been saying. So you can map functions of one argument over lists.
Yeah. Again, references for Haskell or
Right.
introductory textbooks will have all this in it.
So here's a pretty key line of the step sequencer we'll take a look at using a list comprehension. And we see here's that element infix operator in back quotes. So if x is an element of the list of x's, then we'll call a perk function. So perk is just a percussion function. It takes some value p that's part of the bounded set of all the different percussion sounds that we saw in a previous slide. And then it gives that a duration of a quarter note. Else, it gives it a QNR. And QNR is just a quarter note rest. So this is building up something nice. We have a list of elements, and we'll loop over some list from 1 to the max value of our step sequencer. And when we're at a particular I in that list of 1 to the max value, if that I is a member of this set created in this function, well then we turn it into a percussion note. Otherwise, we just play a rest, which is to say we just remain silent. And we can see here that in this list comprehension syntax, x is populated by this list constructed 1 to the global size of the sequencer.
Yeah, the basic syntax for list comprehensions is bracket, value involving some variables, bar, possible values of the variables themselves, close bracket.
Right.
And if you've done set builder notation in any sort of mathematics class, you might have like set to n such that n is in R, or like this n is in Z. Same similar thing. This notation is meant to be suggestive of that mathematical notation.
And you can apply multiple predicates
Yeah.
and multiple filters in a list comprehension, which is quite nice. Algebraic types, we won't linger long here. There's not a good notion in Haskell or a good obvious notion of how to take, say, a default parameter to a function or something.
Mm-hmm.
In Python, this is quite easy. You can just say with equals in the declaration of the function a default value in case none is supplied. In Haskell, you could maybe use the maybe type, which takes either nothing or a value of type just a. So we exploit this in the drum machine to allow us to give optional volume parameters to each of the drum parts. So that gives us a kind of way of having a EQ or volume on a particular channel.
Yeah. In other Haskell examples, you might see maybe used for functions that might fail.
Right.
This is a common one.
Yeah. And you can supply some sort of error message as a default.
Yeah.
And that's particularly handy when you're doing the I/O in Haskell. Can be tricky.
Or, for a simpler example, think of a function that involves division by a parameter that might be 0. Then that function could return maybe whatever. So if there's no division by 0, it will return just whatever. And if there is division by 0, it will return nothing as a way of signaling the error. Because one consequence of Haskell's very strict typing is that there's no real exceptions are awkward, basically. Error handling is awkward. And this is one very common way of doing it.
So now we get to another sort of mind-bending thing about Haskell, which is pattern matching in function definitions. I showed you in the last slide the sort of declaration of the step sequence function, which took a maybe value, then an int, and then a list of ints, and then returns a sequence of music values that are annotated with both pitch and volume. So that those three arguments can be pattern matched in the following way. And we always want to be sure to do a kind of base case or exit case first. And these underscores can just be interpreted to mean sort of any value that's there. So if we get a call to step sequence with some value, some other value, and then the empty list, what we want to return is just silence, a rest 0. And instead of that being the empty list or 0, it's a rest 0 because we're dealing with the music type, and the sort of empty list of the music type is just a rest of no duration. It's no music. And then we see if we get a step sequence with a V for volume argument, P for percussion instrument argument, and then a list of X's. Then we do some stuff. In particular, we apply this list comprehension, and we perform some operations on the maybe value to turn it into a numeric value, so that can be then enumerated and used to select the instrument. Again, this is a little bit deliberately inconcise, just to show all the weird things you can do in Haskell as you kind of take a look at it on your own time. All right, so we're finally getting to do what we set out to do, which is make some computer music. So we're going to try to make the Frère Jacques song. So there are how many phrases in Frère Jacques? 4? Great. And what's nice is that they're all repeated the same amount of times, which is 2. That's right. So we have 4 phrases, each repeated 2 times. And in particular, they're in a round. And there are many, many ways to implement a round that could be fun to do. I've done it in a pretty simple way here, which is just to construct the line function takes a list of music values and turns it into sequential composition by applying that sequential composition operator. And then I delay the different parts by making them begin with a rest. So I start with a rest of 2 measures, and then a rest of 4 measures, and then a rest of 6 measures, and then the round works, as we sort of all know this song. We see 2 sort of annotations or modifications of the music values that are contained in this sequential arrangement of music elements. We have an add volume. This is a function to annotate music with a particular volume. This is a good example of a MIDI signal running from 0 to 127, the 7 bits of information that can be carried. And then we saw it really briefly, but the general MIDI list of all the different instruments. And there's not a whole lot of them. If you use a digital audio workstation like Ableton Live or Pro Tools or something like this, there's an incredibly wider range of synthesizers and VST instruments. But the MIDI standard only has a few, or several dozen. And some of them are funny. Like, I thought it'd be fun if we played the instrument, the MIDI instrument helicopter. And then the next way through the round, we did a pad synth. And then this kind of corny lead square wave synth. And then voice ooze, which are a little bit indistinct on my bad MIDI synthesizer, but they do okay. And then we see this let and in syntax from Haskell. And then we're playing all these parts together with the parallel composition operator. OK. And we could probably show some of this. Here's the code. And you can see in C, there'd be a lot of sort of throat clearing and setting the table code before you could make music like this. Or any other programming language, you probably have to interact with some sort of library or API and set everything up, and then you'd have to clean up. But here in Haskell is, I think, once you get the hang of it, incredibly readable and very expressive. So there is the implementation of Frère Jacques. All right, now we want to add percussion. And this is a little bit messier. So let's take a look at the slides. What's the, do you know the? F5 or something? Ah, there we go. So the big idea is to make a bunch of lists or parts. On those roll-in machines, there were typically about maybe 8 to 10 rhythm or percussion parts. And then use a bunch of techniques. And we've talked about these using folds, filters, lambda functions mapped over lists to generate values in some range, 1 to R. R is 16 or 32 steps in the sequencer. And then, if there's a value in that list, as we're running through the sequencer, running through it over and over, it sort of turns on that note. And that sample gets triggered. OK? And yeah, here are all the different weird ways I came up with to generate notes. Try it on your own, send me some, it'll sound cool. Time permitting, we'll go through this. But for right now, I guess we should demo what we have. Hope this goes OK. So this is GHCI. I'm going to load a file I have called song.lhs, which is the file I just showed you. OK, great. As Connor said earlier, it compiled, it type checked, so I can breathe a lot easier. It's not gonna blow up on me. I did want to show you something useful. You can see that a module loaded called CS50. You can browse that module, and this is so nice about doing. Maybe what you're doing in Haskell is not called software development, but you can do a lot of fun stuff on your own, and the workflow is really nice as compared to a lot of other languages, because you can see in a really readable way what's going on. So we see that we have all these phrases, which are lists of music pitches, and then we build these up into something larger, which is a music song. It's a musical unit, and then we can play this all with a function called play music. You can see that down here, which is just play. I should say, I didn't talk about this $sign that's everywhere. The $sign is another infix operator, but it has the lowest precedence of any operator, which effectively means that everything on the left of the $sign and the right of the $sign, we're going to get evaluated before it. So it's sort of like another way of adding parentheses.
Yeah. It's basically function composition.
Yeah.
And it ensures that you don't have, if you have functions on either side or infix operators on either side, they won't associate across it and give you unexpected results.
So we can, using that, we can call, first we'll play it without the drums. That's the helicopter, the MIDI helicopter. There's the square wave. The voice ooze. And you can really go wild with this. Like, I picked a pretty simple one because I knew I shouldn't bite off more than I could chew, just keep it pretty simple to show the main ideas. But then I was like, we've got to add some drums to this. Just because this is a little bit impenetrable, and I didn't use the name of the drum parts. I mapped them, because they're part of that enumerated class, I mapped them to ints. 1 is like a bass drum, 0 is as well, 7's a hi-hat, and down in here, where the functions get a little more random, these are like conga drums. So if you think about maybe a fun way to implement a drum machine is to use very orderly patterns on your bass drum. So for instance, I'm filtering over the list with everything that gives back a 1 when it's taken modulo 4. So I get 1, 5, 9, 13, 17. So this is like the first beat of every measure, right? And then this is the same thing shifted over 2 steps. So that's the off beat. So this would be something like a hi-hat, right? Mm-hmm. And then again, down here, it's a little more random because we're doing like conga drums. And I have some maracas down in here too. So I could call play drum machine, but it would go on forever, and it might start grabbing up all the memory in my system. So I'll call this function play music, which, as we'll see, use the truncating parallel composition to play our little Frere Jacques song along with this weird drum machine. So let's take a look, and please do improve on my arrangement of all the drum parts. Not my specialty, but I had a lot of fun doing it. All right, cool. So, of course, this is all a little bit not as fun if we can't convert it to a score. So maybe it can be interpreted by a human performer. So I won't run it here. I've already generated the files. You can see that there's a .lilypond file, and this will be my segue over to Connor, and a .mini file, and a .pdf file, which is what Lilypond will ultimately generate. But these are those scripts, and I'll just run them with their sort of help options. If you get these up and running, with Euterpea, you can generate a MIDI file. And then from the MIDI file with this MIDI to LY program, you can generate a Lilypond file. And then you can generate a PDF of the score. And we should take a look at this. Where is the PDF?
Song MIDI.
Oh, yeah. So Connor will probably show you how to annotate this better. But this is Sverajaka as generated by me in Euterpea. It's just in C. I should have figured out what the heck it's actually in. But that is the pipeline for how you do that. With that, let's talk more about Lilypond.
OK. Let's see. Yeah. All right. Did you mention Learn You Haskell and your resources?
Oh, yeah. Check out Learn You Haskell. It's in the resources. That's sort of how I started learning, and it's great.
Yeah, it's a
Not done
textbook. It's online. So a guy named Miran Lipovaca. LearnYouAHaskell.com, just no spaces. Grammar is sick.
Yeah. It's illustrated, too.
Great. So what is Lilypond? It's a declarative programming language for music typesetting. So declarative, you can think of things like HTML, where you're not saying how HTML doesn't say how web browsers should render web pages step by step. It's just saying this is a textual description of what you want the page to look like. And then it's also a program that compiles this language, or it reads it in and then actually does the typesetting for you, and it spits out these wonderful-looking PDF scores. You can also get them in PNG format or whatever. Good way to think of this as by analogy is that LaTeX is sort of like Lilypond, but for just ordinary typesetting. So instead of it's not WYSIWYG, what you see is what you get, like, say, Finale is, or Sibelius, or Microsoft Word, where you can type in real time and drag things around in real time and see changes instantaneously. It is text-based. You have to compile your scores using a separate program and get out PDFs later. This is a bit less convenient for use if you're trying to write directly into a score and you're trying to compose on computer. But there are a lot of advantages for it. One, it does look a lot nicer because Lilypond can actually take the time to do layout decisions properly, unlike Sibelius or Finale, which sort of have to make compromised algorithms so that they can display things in real time. So why use Lilypond? Computer graphics is hard. If you're doing anything with music and you want to write out scores, you don't want to write out everything by yourself, starting with like how to draw staffs and how to draw note heads. It's very difficult. It's been done before. You're fine. If you want to use Finale or Sibelius, the file formats for those things are very complicated, and you can't really use them programmatically. You can open up Sibelius or Finale and go to File, Export as PDF yourself, but you can't really call that from a script. Lilypond you can call from a script. It's actually pretty easy to integrate Lilypond with LaTeX. I won't have that much time to go into these technologies right now, but they exist. If you want to look into Lilypond Book, it's a program that comes with your Lilypond distribution, and it's for integrating Lilypond fragments into LaTeX if you want to do something like a big musicology document with examples, for example. And it's a good skill for life if you're doing anything with music, not just CS50. I've used Lilypond for all of my composition projects since I was basically a senior in high school. So here's some simple examples. These are some this is basically representative of the level of difficulty that most people would face if they're trying to use Lilypond for just simple projects. This first one is the beginning to a chorale prelude by Bach. This bottom one is an excerpt from my own works, and it's just there to show you things like more clearly putting multiple lines in the same staff, how lyric undersetting works, or lyric underlays are a thing. It's very easy to use the Lilypond for choral music. And so then there's some more complicated examples here. All these are done in Lilypond. They're feasible. This first excerpt is from Goyescas by Granados, and this bottom excerpt is from a piece for solo bass flute by Trevor Basha, who was a long-time member of the music department here. I think, not sure where he's gone off to, but he was the advisor of the Harvard Composers Association for a long time. Wonderful man, and he writes some music that has very complicated notation that Lilypond can nonetheless handle very nicely. So, just to give you a sense of what this thing's capabilities are. So the internals of Lilypond are very complicated, and you can use it for a long time, including for some pretty complicated things without really having to know a lot about them. But the basic idea is that on the lowest level, the atoms of Lilypond sort of are the notes. And the notes get contained in context called voices. So the voice context basically corresponds to a single line of polyphony. And then context can be contained hierarchically in higher level ones that represent staffs on the score, or larger groupings like piano staffs or choir staffs, and then eventually entire score context, and you can actually encompass multiple scores in a book. And every context has a number of attached engravers that basically look through the contents of a context and print a certain symbol or certain class of symbols as necessary. So to every voice context, there's attached a note heads engraver that is basically a function or an object that writes out all the note heads on the right parts of a page. Then there's a clef engraver, which writes out clefs on the staff. Then there's a metronome mark engraver that writes out metronome marks on a score. And all of these fit pretty well into the hierarchy. And it's very, very, very customizable, which you need if you want to get things like that. So all of the contexts have a lot of different attributes that you can modify for everything from spacing to various font selections to just sizes of things. If you want to do even more complicated things, there's an embedded scripting language. They use Scheme, which is a dialect of Lisp. These probably don't mean anything to you, but basically Scheme is another functional programming language, more or less.
The tie-in.
Yeah. Yeah, it's a good tie-in, I suppose. And it's used as a teaching language actually down Mass Ave at MIT. And it's very handy for Lilypond for various technical reasons. And so if you want to make simple tweaks that depend on conditionals, for example, if there's a certain condition in the score that's met, make alterations to the layout or whatnot, then those facilities are there. They're complicated. So here's a pretty simple code sample. It's 5 lines. Basically, I'm defining 2 staffs. It's in 3/4. First staff has an attached tempo mark, but that's actually going to go onto the whole score because tempo marks are on the score level. The metronome mark engraver is attached to score context. They're in different keys because the key signature engraver is attached to staffs. You can actually do this. The sample I wrote is actually in C major, but it's just to demonstrate you can have different keys and different staffs. And the basic syntax is you write note names with E, F, G, whatever. If you want to do accidentals, you suffix IS or ES. This is from Dutch musicological conventions. And to do octave leaps, you have to use these tick marks, like comma or apostrophe. The relative just means whenever you have a note, it will automatically be placed in the octave closest to the previous one. And if you want to jump more than a fifth, or I should say a fifth or more, then you have to use these octave transpositions. But otherwise, you don't have to specify the octave of every single note. And then relative C, prime, and C to specify middle C and bass C, respectively, for the first notes. Then you have these staffs that organize these 2 voices or samples of music. Then you have a score, and that looks like this. And if you want to take the time to copy that sample of Lilypond code in the previous slide down here, and you can run it through Lilypond yourself, and you'll get something that looks a lot like this. All right. So there's another technology called MusicXML, maintained by completely different people. XML is a textual data structure. I shouldn't say data structure. It's a meta format, sort of. And it's designed to hold hierarchical data very well. HTML, for example, is a type of XML. And you can tell XML because they have all the angle brackets and angle bracket slash marks that show data fields. I don't have an code sample for MusicXML. You can find yourself. basically, the reason you might want to use MusicXML as an intermediate stage is, first of all, it's an interchange format for basically I shouldn't say every, but a lot of different score writers. So if you write out MusicXML, not only can Lilypond read it with the help of this auxiliary program called MusicXML2ly, but also Finale can read it, Sibelius can read it. Depending on how your internal object hierarchy works for representing music, it might be easier to write out to MusicXML than to Lilypond, and just rely on MusicXML2ly to do the conversion. I don't think Euterpea has a MusicXML.
Does not. Someone's working on it.
Okay. Euterpea does not have a MusicXML output function yet. If you want a final project idea, I don't know, maybe get in touch with the guys that Steven knows, and they could use your help.
Yeah, we'd love it. Love that.
Yeah. Also, basically every programming language that's worth its salt already has an XML library, so you can internally convert all of your music into some object that the XML library can write out. That might require fewer alterations to your internal structure for whatever music objects you want to write than writing it directly in Lilypond would. Then just print it out with XML, with the XML libraries in your language, which will guarantee that it's syntactically correct and everything, and then convert it to Lilypond. So technology you might want to look into if you're doing something like this. Frescobaldi, another auxiliary technology. This is just, it's basically TechWorks or Tech Studio for Lilypond. So it offers help with syntax, with templates for various common combinations of instruments. It allows split screen viewing, so you can have your code in one window and PDF in another window, and click on places in the PDF to jump to the relevant spots in your source code. This is more useful if you're actually writing Lilypond files yourself than if you're generating them programmatically. But again, it's something useful to have. Great. Another resources. I'll just go through this very quickly. Lilypond manuals. Lilypond has an excellent documentation on its website. They have a tutorial, they have a syntax reference, they have hundreds of snippets for various small things you might need to do or to demonstrate various capabilities. If you want to use the scripting language or make more extensive customizations, then there's an internals reference at that URL. If you want to use MusicXML, there's that URL, musicxml.com/tutorial. And then if you need to learn Scheme because you actually are using going to use the scripting facilities in Lilypond, then there's this book called Structure and Interpretation of Computer Programs, which is not only the second greatest CS textbook ever written. Find me afterwards if you want to know what I think the greatest one is. But it's also a very good introduction to the language proper. You won't need more than the first few sections. Great. And that's it. Any questions?
Where can I download your generated for Jacques? Put it on my iPod.
Well, you can write out to some wave file in Euterpea, and you have the code. It's on GitHub.
Awesome.
Make your own variations on Frere Jacques by CS50 Hivemind would be great.
Sounds good.
All right. Anyone else?
We need a better bass drum too. It's
Do
really
you have a question,
bad.
sir?
Yeah, so Euterpea has not only the sort of composition side, but signal processing.
Yes, in fact, the work I did in Euterpea when I took this, there's like a graduate course at Yale that uses it, was on sound synthesis. So there's a really nice way using arrows and some of the notation we saw of composing together signal functions. In particular, the base for most of them is just a simple sine wave. But if you start composing those in weird programmatic ways, you can get crazy sound effects like weird cascades. You can create very gritty sounds with a lot of modulation. I did a project on granular synthesis, which is somewhere in between FM and sampling. You take very small little samples and then combine them with some sort of modulator and build up a richer sound. We also did physical modeling, so trying to think about the physics and psychoacoustics of something like a trumpet, and thinking about the way the sound is bouncing off the bell of the trumpet and in the acoustics of the room, and modeling that with kind of basic oscillators.
Anyone else? All good? Okay.
Thanks
Thank
so
you very
much.
Thanks for coming. And I'm always willing to take questions by email, connorharris@college.harvard.edu.
Yeah, Steven.Krewson@yale.edu. Cool.